Oh, hello everyone. Welcome back to another Learning Glass video. So here in this video, we'll talk about burning a carbon particle solid fuel and using two-film model, which is a one step above detail than the one film, just like one interface. Here, there's the surface that has some processes we are going to consider, and then the flame is another interface to consider. So if this will be our carbon particle here, carbon particle, solid, so there's no fuel this simple as carbon. Carbon is a very useful material, graphite, amorphous, different types of solid phases of carbon are very useful materials, but they're not real fuels. In terms of burning of this carbon particle, it's a very simple model to start to understand coal burning perhaps, but even coal is much more complex, and it's not only carbon, and it's also, there's a lot of details of the solid burning itself that are very important as well. So in this simple model for the two film, we're going to consider that there is a surface reaction. So instead of vaporization of a droplet particle, a liquid droplet, it's going to be a surface reaction which results in the formation of CO, carbon monoxide, from the surface. That carbon monoxide is then the fuel for the flame, the diffusion flame. So here we have a diffusion flame. So this will be flame, and it burns from air diffusing to the flame front from the surroundings. So this film is the surface, this film is the flame sheet at some given radius in radial coordinates. So what's happening here is you're going to have two different interfaces. So let's draw this being a position in radial coordinates. So if this was from the center line, some radial coordinates out, and either the temperature profile or the species profiles will have these certain characteristics at these two different interfaces. So let's call this, so this would be the radial position of the surface, how big the particle is, and this would be the radial position of the flame. So at some distance away from the center line, you have the flame sitting there, at some distance the surface from the center line. And what happens is there's two interfaces, two films. The first one, it's a chemical reaction between the surface and the gas phase surroundings. And the specific model, the reaction, which is again a simplification, but so it'll be carbon surface plus the CO2 coming from the burning product. So this product of combustion is CO2. So that CO2 back diffuses or back flows, leading to the production of carbon monoxide at the surface. Then the fuel for the flame, it's this CO. So the CO, two CO molecules plus one O2 molecule goes to two CO2 molecules. So the CO is like, chicken and an egg thing. Once you get it lit, it establishes this process where you form CO at the surface. That feeds the flame. That continues to feed the flame. And then when you burn the CO, it produces CO2. That keeps the CO forming from the surface. So that's what's happening. And a typical profiles look like, if this was the surface of the temperature of the surface, it'll be simplifying it to be some constant temperature inside the surface. Then as the at the surface, there's a chemical reaction leading to CO, and then burning upstream then that temperature, that would be the flame temperature, then it'll go down to whatever the ambient temperature is. So this will be the temperature infinity, this will be the temperature of the flame, the hottest point, and that will peak out at the flame sheet, and this will start to increase at the surface. So that would be the temperature. And what's happening is you're producing CO2 at the surface. So if this would be the concentration of CO2 at the surface, it doesn't exist inside, but it jumps off of the surface. Then, because of diffusion, it travels from where it's produced all the way to the reaction zone of the surface reaction. Then it dissipates in space. It diffuses out radially. So this would be the CO2. Then you're producing CO at the surface. And so that's the reaction to convert CO2 and carbon to CO. And so you have some high concentration here, but then it all burns at the flame. So it goes to zero, basically. Maybe I should draw that to zero. It should go to zero. So this would be the Y, mole fraction of the CO burning at the flame. And with oxygen, it's the opposite. It's coming from the opposite directions, from the surroundings, from the air, and it diffuses in. So there's some far stream O2, and then it all gets burned at the flame. So that's what's happening. It's you have a flame set up, a high temperature, and what you're doing is you're burning CO completely. That oxygen from the surrounding air also gets consumed. And again, it's like we're assuming the flame is already going. Once the flame is already going, you establish this feedback, this transport and steady process where the CO2 you're producing from burning CO feeds back into the surface to oxidize oxidize the carbon to CO. Then once you form CO, it burns and it feeds the flame. So that's what's happening. That's the two films. So in terms of a mass balance, the CO2, like we were saying, it gets produced in the flame. So if this were the inner region, and this were the outer region, the CO2 produced in the flame will diffuse into the inner region and out to the outer region as well. And then you have some flow rate of O2 from the surroundings. Then you're producing CO at the surface, and that goes to feed the flame. And then this whole source of the carbon is the carbon surface. So it's not really flowing, but as soon as you leave this surface, it is you can use it to balance the carbon, because even though it's not moving, there has to be a mass balance to keep all of this balanced out based on the surface carbon. Then, in terms of energy, at the surface, you have a surface exothermic oxidation of carbon that releases, that leads you to a temperature increase. And as the temperature increase, you have conduction in of energy. Then you have also going out by conduction, energy transfer. So that's energy. And then because of it's a solid, a dense solid, at some reasonably hot temperature, you also have a release in energy outwards by radiation. It's glowing hot, and as it glows hot, it loses energy by that radiation mechanism. radiation. And then you also have the energy of each of these flow rates. Again, this is not flowing, but it does carry energy that we have to balance. So this would be the sensible energy of the mass flow rate times the enthalpy of that molecule of the carbon. That's coming that direction, and then coming out, also coming out, it's the CO that you're producing. And then coming in, it's the CO2 from the surface, from the flame sheet to feed So there's another, so that's the energy balances at the surface. There's another balance at the sheet. We don't need that for to gather most of the equation. So what we're trying to solve now is what are all these flow rates involved? What are all these concentrations? The CO2, CO, and the carbon. And what is the temperatures? The temperature of the surface, the temperature of the flame, the temperature downstream. So depending on the problem, you may know some of these flow rates. Like you might know of course, we probably know the air concentration at the far stream. You probably know the ambient temperature or some furnace temperature or something like that away from the particle. And from all of these balances of mass, species, and energy, we can try to solve the governing equations to get a feel for all of these parameters of the process. So with some simplifications, again, one of them is being steady. We're ignoring the ignition, we're ignoring any transient heating and stuff like that. We're going to say we just already set up a field where a flame, it's established, and there's a balance between the CO produced, the CO burned, the CO2 coming back, and we can go from there. So let's start. I'm going to erase this just to give us, this would give us a good diagram. But the goal is to consider this surface reaction, consider the flame away from the particle, and in terms of all of these, the mass balance, species balance, energy balance, to get what we need to get a good model to try to analyze what's going on. Okay, so let's start off with the stoichiometry. So if this is a surface reaction, what's happening at the surface at the radial position of the surface, there has to be, in terms of mass, a balance between, for every 1 kilogram of carbon that is consumed, and a stoichiometric balance, you have to have 44 over 12 kilograms of CO2. So 44 is a molecular mass of CO2, 12 is the molecular mass of carbon. So it's basically saying that if you're going to produce CO, you have to balance this like here. So this is not balanced. This should be, I guess, 1/2 CO. Should be 2, 2. So that's what this is doing as well, but just in terms of mass. That's going to go to 44 over 12 plus 1 kilograms of CO. So that's balancing atoms as well, but just converting to mass, which is nice because mass flow rates are more measurable. So that's going to help us with our mass balances to try to tie all of this together. Then at the flame, we can also use a reaction. So at the flame, it's going to be burning CO to make CO2. So in that terms of that, per 1 kilogram of carbon. So before we do that, we're going to use mass balances. So we're going to substitute CO flow rate with C. So using these mass balances here at the flame, we can manipulate them to express the fact that the carbon comes from here and it forms CO2 along with this balance. So this balance can help you to analyze this balance. And to simplify, we're just going to go straight to express all of the mass flow rates in terms of carbon. And as long as we can tie them together here, we can get all the flow rates. But I'm just going to show you that we're going to work in terms of carbon to skip some steps, that we are using these balances, and then at the end I'm going to just show you how they are related to the carbon flow rate. So if you do that, then for every 1 gram of carbon that burns at the surface, tie it to CO at the flame, that you need this -1 of O2, and that will lead to so again, this ratio is just converting mass to moles according to the molar mass of CO2 and carbon. Then, if we are going to so we have these, what we see here is that these reactions, balancing the atoms and then converting to mass from atoms to moles to mass, we see the stoichiometric relationships here. So let's define, let's call it nu of the surface, the stoichiometric coefficient of the surface, that is 44/12, because we're dealing with CO2, we're reacting with carbon at the surface, and then the stoichiometric coefficient of the flame will just be related to the surface, 1 minus 1. So these mass balances at these two interfaces, these two films, are expressed in terms of carbon after doing these mass balances. And then that shows us that we have these coefficients that have to hold to conserve mass. Okay, so let's move on to the species. So we're going to have CO2 that we need to track. That's being formed at the flame, and then it is used to oxidize the carbon. And let's write the species equation, which without any bulk convection has just transport by diffusion. And that's one form of the Stefan problem that we've worked on before, and radial coordinates. So it's similar to the evaporation, transport, droplet evaporation, and droplet combustion models that we've worked with. Okay, so species, again, so this is the stoichiometry, then the species balances, again, in terms of the C flow rate. So I'm saying flow rate because it's just some kilograms per second burned at the surface, but that has to balance the flow rate of CO2, the flow rate of CO, and all that stuff. So all of these by mass conservation are tied together. To skip some steps, I'll just show you at the end, you can tie these all together by the m dot of C, m dot C here. This is how we're going to express all of them here. And so in the inner region, you have CO CO2 coming in from the surroundings to the surface. So that would give you diffusion without any bulk flow. So again, expressing the CO2 diffusion and simplifying it just to the MC by mass conservation, this should be like the Stefan Boltzmann problems. So this is tracking the CO2 coming from in the inner region, from the flame to the surface. So the CO2 anywhere in the inner region, and that has to balance according to this stoichiometric, this ratio stoichiometric coefficient at the surface. Then you have this diffusion component. So that would be the CO2 in their inner region. Next, let's do the outer region. Again, expressed in terms of the carbon. So it's flowing in a different direction, the CO2. So here, the stoichiometric of the flame comes into play. Okay, then we have air. This is actually going to consider the fact that this is air in the surroundings. That gives us another governing equation. So from N2, that has to balance out, so we can also express the air in terms of the carbon. And that would be okay, so these are the governing equations of CO2 and air from the nitrogen from the air. And if we apply the boundary conditions at the surface and the boundary conditions at the flame, that can give us some expressions and solve these ordinary differential equations. So after applying boundary conditions, we should get that we have three different expressions of carbon. By mass conservation, we're able to express the CO2 flow rate, CO flow rate, nitrogen flow rate in terms of carbon. And applying the boundary conditions, these all should balance out each other. So the solution to these ODEs will be some algebraic expressions, some analytical expressions that we may not be able to solve on paper, but we don't need a ODE. We've already solved the ODE, then we just have to solve these resulting algebraic expressions. So in chapter 14, there's a little bit of discussion. I mean, there is more discussion, of course, but it builds upon the droplet combustion model. That droplet combustion model builds on the droplet evaporation model. So building from these discussions, we arrive at this final model, which is still oversimplified, but it does capture a lot, and it is very instructive. So when you apply those boundary conditions, you should be able to get that the mass flow rate, which is basically the burning rate of carbon, equals 4 pi, that's the spherical coordinates, but when we apply these boundary conditions, it's going to give you that some boundary parameters like the radius of the surface, the radial position of the flame, and this difference between the flame position and the radial position, that's like this distance here. Then this diffusion behavior of the mixture in the inner region, and this big natural log, not too big, but so whatever the CO2 concentration of the flame is over this coefficient in the flame, let me double check this one real quick. So let me get this from chapter 14. Yeah, so both of these are dependent upon the coefficient of the surface according to this analysis, which I have to think about that, but that's what the book has. Might be a typo. I'll have to think about that, but let's go with that for now. And then we also had a balance. So this would be the balance of CO2 in the inner region. We had a balance of CO2 in the outer region, and we also had to use the nitrogen mass balance. So you can also get, this should equal the outer region. So similarly, you can get a second equation in terms of mass using the outer region, and that is flow in a different direction, and that gives you related to the position of the flame, this diffusion behavior in the outer region. So I guess what we're doing is simplifying the stoichiometry. Whatever the concentration of the flame is, and then the surface. So I guess they're minimizing. It probably does give you some dependence on the flame stoichiometry, but we're simplifying this only in terms of the surface stoichiometry. But nonetheless, we now have two equations for the mass carbon, and that helps us to solve the problem for any of these variables that we might need. The CO2 at the flame, the CO2 at the surface, the position of the flame, the position of the surface, and the mass flow rate of the carbon. And the nitrogen mass fraction should also pop out of these. So that would be, depends on the far stream. So the nitrogen is not reacting, but because of all this shift in moles and molecules, the mass fraction and mole fractions changes because not nitrogen doesn't change, but everything else changes. So that changes the proportion in the mixture of nitrogen. And that helps you to pin down the mass flow rate of carbon as well. That gives you another equation for the burning rate. Okay, so we've made a lot of progress so far, and I'll draw this up top. So what we did was we expressed all of these mass balances and species balances in terms of the mass flow rate of carbon. And it's not a flow rate, it's more of a burning rate. It is a flow rate in terms that you have to balance all these flows with this rate here. And it's not really flowing, but it is burning. It's converting from C to CO. Because of that, that affects all these other balances. So this is what we express all these balances here for. And if we were to combine all these, what you should get is, it's like a super long algebraic expressions with all these parameters, mainly from the boundaries. And what you should get, it's combining all of these, and then what you can be able to do is combining and get a lumped expression. Let's call this the burning rate. Burning rate. In terms of all this analysis, it's dependent on the radial position, the diffusion of the mixture, the diffusion behavior of the mixture, and the this expression here, this B number. Some B transport number. So what we've done was combine all these equations to get a more compact form, and we compacted a lot of this transport behavior and stoichiometry balances into this B, which is related to the stoichiometry occurring at these two films and the flow rates of oxygen, or the mass fractions of oxygen and CO2. So this is the burning rate. So it's a burning rate that has to balance off all these flow rates. That's how we were able to link all these together. And at the end, we get this compact expression, and this ratio, this B transport number, it's related to CO2. So depending on the far stream oxygen concentration and the stoichiometry, so it captures this reaction, and mainly so far the diffusion behavior. But another thing that's happening is you have both a surface reaction converting carbon surface to CO fed by CO2, and you also have gas phase combustion of CO gas to CO2 by the surrounding oxygen. Okay, so let's consider that. So let's assume that gas phase reaction rate, it's much, much faster than surface reaction. So that means it's only the diffusion limits this. Once it reaches there, it's going to convert. And this is the slower, this is the bottleneck. So if the gas phase reaction rate is much faster, then we only have to worry about, this is the only one we have to analyze. So for the surface reaction, this would be the conversion of carbon solid plus CO2 gas goes to CO gas. And I don't know if you guys remember that for equilibrium and kinetics, that unless everything is in terms of one global way to model this, it's only dependent on the gas phase, because the concentration of atoms is much higher than, they're so dense that it only depends on how much gas you have. So this would be the surface reaction rate of carbon solid. It only depends on, it's a rate coefficient of this combustion times the molecular weight of carbon, and it's first order in CO2. It only depends on the concentration of CO2, and this is by the ideal gas of CO2. This is P over R, the universal gas constant, equals NCO2 over V. And the partial pressure. So using that, we can get that based on the surface reaction rate, we can get another expression for the burning rate. So converting the surface kinetics to the kilograms per second by using the ideal gas law, by using this first order reaction rate of this surface reaction, we can get this based on the surface kinetics. We have this kinetic rate coefficient here, and then balancing all these molar masses. Here it's the surface temperature and the mole mass fraction of CO2 at the surface. All right, so that gives us another reaction. Now, let's do the energy balance. So, the energy balance will give us more temperatures. What's happening is we have a surface reaction that is going to increase the temperature of the surface because it's exothermic. And then that energy is going to conduct into the particle and out to the surrounding gas. Because the surface is glowing, we have radiation losing energy from the surface out to the surroundings. And then there's these other sensible enthalpies of the carbon, the CO, and CO2 that takes energy to raise or decrease the temperatures of those molecules. So that's the energy balance. And let's see, I'll do that here. So this is from the surface kinetics. This is from kinetics of surface and there's basically no kinetics of the gas phase because it's much faster than the surface. So as long as you know the surface kinetics and the transport, it's just going to be a conversion instantly at this film of the flame. Okay, now let's do the energy balance. So assuming that Q conduction in is 0, we're not going to worry about conduction through the surface because we've already assumed that it's just a constant temperature. So for there to be conduction, you have to have a gradient from hot to cold. Here we're just ignoring that it's just going to be one constant temperature, which again is an oversimplification, but it'll still give us an interesting usable result. So we're going to have this term 0. So the energy balance would be the burning rate of the carbon times the enthalpy of the carbon has to balance with this enthalpy of the CO2. That has to balance with the temperature change related to enthalpy. These are all just related to changing the temperature of these molecules. The CO is coming from the other direction. That should be a minus. It's coming opposite directions. And then we have some heat loss by conduction from the surface to the surroundings. And you also have some energy loss from the surface due to radiation. That all is at steady state. So that's the energy balance. That's the energy balance. And that should allow you to give you this balance of at the end, that the mass, the burning rate of carbon times the enthalpy of combustion of carbon equals this balance here where it's this conduction effect. So we're just applying the Fourier's law of conduction here. So the conduction balance at the surface, and then the radiation, Stefan Boltzmann law. So this is the radiation model, and this is the conduction model at the surface, and the radiation at the surface has to balance out this enthalpy of combustion, this chemical conversion exothermic process at the surface has to balance the conduction and the radiation. And then, so if we apply boundary conditions, we're going to get a big monster that I have to make some space for. We're going to, similar to the droplet burning and these other analyses we've done, we've had this, mass transfer numbers and this resistance and, circuit analogies. So if we were to define this thermal resistance-like thing here, this ratio would be the heat capacity of the gas over the conductivity thermal conductivity type behavior of the gas. So we had a chemical kinetics, that's from the chemical rate coefficient. This is the thermal conductivity of the gas. So defining that, we can get this big expression here that the burning rate of the fuel times the enthalpy of combustion all has to balance all these other effects here that I'm about to draw out. Again, the burning rate of the fuel, again, it's all these big, they're algebraic and analytical to some extent, but they're pretty nasty. Here's this resistance here. So we have a surface, depends on the temperature of the surface, and then this is all multiplied by the temperature difference between the flame and the surface. Then you have these so-called resistances here. So this nice resistance ratio here is captured, is giving you this ratio between the thermal capacity, like the response of the coefficient of temperature and energy. That's what CP is. The proportion of temperature to energy, and this is how fast energy can transfer by heat transfer by conduction. So yeah. This is considering, and then all of this would be like more of the conductivity, heat capacity thing. That all has to balance off plus a radiation behavior. So here's the radiation. So this is radiation, and that has this classic Stefan Boltzmann model of this radiation to the fourth. So that whatever the glowing surface temperature is, and the difference to the fourth power with the ambient temperature in the surroundings, that's how the radiation energy will transport at that rate. And then here you have this conductivity of the gas, depending on the heat capacity of the gas. So this would give you the energy balance. So here, this energy balance can give you the flame temperature, the surface temperature, and the burning rate. And again, collapsing all this with the mass flow rates and the transport by diffusion, you can get this compact form. And that is all combining all of this other analysis we did, all these other balances. And that should give you how all of these are connected. So in chapter 14, this equation here, so this would be 1453, 1454. So these are like kind of the final results here. This is my gift to you. My gift from my generosity. This is an energy balance coming from this, having a lot of assumptions, a lot of the analogies we applied for the droplet burning. But at the end, what we're trying to find is so all of these equations and what this problem is designed to find, it's not even the profiles in space, it's just the boundary conditions. So in this simplification, it'll just give you the boundary conditions. So what you're trying to find is the burning rate, the mass fraction of CO2 at the surface, the mass fraction of CO2 at the flame, the mass fraction of N2 at the flame, and the position of the flame, the position of the surface, and the temperature of the flame, the temperature of the surface. So we may know some of these boundary conditions, we may not. Depending on the problem, we can use this analysis to find more details as we need. So we skipped a lot of steps, of course, because it's it's a lot of analysis and a lot of steps. But the idea here is that this would be a solid carbon particle, which is an oversimplified solid fuel, but it's a good start. Coal is much more complex in both the chemistry, it's not only carbon, there's a lot of stuff in there. And it's also, for any real coal combustor, we have to worry about the details of what's happening inside the particle. That is a large part of the combustion of coal. And here we're not considering that. But we captured a lot. We captured that the flame itself, one important fuel for a solid fuel that's feeding a flame is CO. And in this model, the CO burns to produce CO2. That CO2 diffuses outwards, meaning outside of the flame. Half of that goes it goes in two directions. In one direction, it's towards the surface of the carbon. The other direction is to the surroundings. When that CO2 approaches the carbon surface, it produces more CO. Then that CO can go on to burn at the flame away from the surface. And then the oxygen comes from the far stream. And by applying these mass balances, we were expressing all of these flow rates in terms of the burning rate of carbon. And that's so we can be able to at the end compact all of these into this lumped equation here, just in terms of the surface concentration of CO2 and the far stream concentration of O2. Then applying an energy balance at the surface, we're able to get another expression of in terms of the temperature of the flame, the temperature of the surface. And then the kinetics of the surface are much slower than the kinetics of the flame. That means the flame kinetics are basically infinity, which means only this one limits the process. And that gives us another equation in terms of the surface position and the flow rate, the mass fraction at the surface, and the temperature of the surface. So that is the two-film model. And with that, I'll see you guys next time. Thank you.